We just spent 100 hours tuning and scaling our n8n RAG workflows. This system imports files into a Supabase vector store for an AI agent to query. However, it's slow. And after this marathon effort, we've reduced processing time of files by a whopping 97%. So we can now import 5,000 PDF files per hour. In our test, this was 10 gigs of data with 250,000 chunks in the vector store. And during this process, we broke everything. We crashed n8n multiple times, crashed Supabase, even the Google Drive node started glitching. So in this video, I'll take you on our journey of scaling n8n and tuning this workflow, sharing both our approach and the lessons that we learned along the way, so you can avoid the same pitfalls when you're scaling your own workflows. As I mentioned, this was a marathon effort, so I'd really appreciate if you gave the video a like and subscribe to our channel for more deep n8n content. Let's get into it. So what are we trying to speed up here? Well, if you followed the RAG masterclass on this channel, you'll know that we have built a fleshed out RAG ingestion pipeline for your AI agent. This pipeline pulls files from Google Drive, and then in a loop, it extracts the data from those files, and then it upserts the data to a documents table in Supabase itself. This pipeline now has over 90 nodes to process a single file, and it is ideal for smaller knowledge bases, but as I mentioned, it is quite slow. It can only process around 100 files an hour. So that was our challenge. How do we dramatically scale this up? The approach we took was for myself and Alan to split the work down the middle. My task was to take the existing RAG ingestion pipeline and to tune it. In other words, figure out where the bottlenecks are in that flow, and then make changes to try to increase the speed of the pipeline end to end. And once the workflow is as efficient as possible, then it's a case of scaling up the infrastructure to see how many files we can get this workflow to process in parallel. Which then leads me to Alan's job, which was to build the orchestrator. Because the RAG ingestion pipeline that I showed you processes files in a loop one at a time, whereas we need to be processing multiple files simultaneously to actually increase the throughput. This orchestrator is essentially a custom queue that's going to be firing off multiple files in parallel into this RAG importer. And this orchestrator also needs to be resilient, so if any of these RAG imports fail, there needs to be a system where it can automatically retry an entire execution. Alan has published a detailed video on how this orchestrator actually works, so I'll leave a link for that in the card above. But in this video, we're going to be diving deep into the journey we went on to tune and scale the system up to 5,000 files an hour. To tune this system, I took an iterative approach. So the first thing I did was to establish a benchmark. How fast is this workflow? And then understanding what the baseline is, it's a case of identifying where the bottlenecks are. And then from there, you can generate a hypothesis. Maybe there's a node in the workflow that's slow because it's a third-party call and you need to scale up resources on the third-party side. Or maybe it's some bloated code in a code node, and the hypothesis is if you can make that code leaner, you can eliminate that bottleneck. And from there, you need to analyze the results and decide whether you want to keep that change or not and go again. To establish a baseline on this flow, I picked a single PDF file that contained 50,000 characters. The benchmark PDF is a 24-page instruction booklet for a coffee machine. And I ran it through our importer. And this included Mistral OCR on this file. And the average time it took to process this file over a number of tests was 26 seconds flat. So this is our baseline that we're trying to improve on. If it's taken nearly half a minute to process a single file, you really will only be able to process around 120 files an hour. So how do you find the bottlenecks? Well, you need to jump into the execution history. And then at the bottom you see logs. So if you hover over the logs and click overview, you can see the amount of time each node took during the processing. And from here then you just need to find the big numbers. So this workflow took 26 seconds to process, and I can see immediately the download file from Google Drive took 2 seconds, uploading to Mistral was 1.5, extracting metadata with OpenAI's GPT-4 Mini took 1.7 seconds, upserting to Supabase took 4 seconds here, took 3 seconds there. So you can figure out where the pinch points are in the workflow, and that's where you need to focus your attention. So the first hypothesis I had was around this idea of processing a single file at a time. So within the blueprint, it all starts with this loop over items. So what I wanted to do was to increase this to 5 or 10 or 20, just to see, can we dramatically improve the throughput through the system? Now this was no easy task because this workflow is quite complex. We have nested loops, there's a lot of mappings to previous nodes, and when you want to increase the batch size of a loop over items node in n8n, you end up needing to use a lot of these merge nodes. So you'll see we have one here, we have another one here, we have another one here. And the reason for this is, let's say you have 10 files being processed in this loop. When we get down to here, where we're fetching metadata fields, or we're just fetching something from a database, you might have 20 fields in the database. So you'll have 10 items coming through here. This is going to generate another 20. Then you have a mismatch of the number of items coming through the loop versus what you've just actually rendered from a node. So it gets really complex, and you need to use these merge nodes to keep everything on track. So with the changes made to the blueprint to support multiple files in a loop, I then carried out a number of tests with different quantities of files, different batch sizes, to figure out, is this actually improving things? Initially, I tested it with a batch size of 1, so we just sent each file through sequentially, and I then tried it with a batch size of 5 to send them all through at the same time. And we did get an improvement. It was nearly 10% faster, but this was nowhere near the improvement that I was hoping for. I then tried it with a batch size of 10 files, and it didn't really make a difference. It was possibly better with a batch size of 5. And finally, I tried it with a batch size of 20 files, and I crashed the server. And in a way, that's no surprise, because within this workflow, we need to download the file to actually process it. So if you trigger the download of 20 binary files, that's going to clog up the RAM to the point where you're going to run out of memory. Now, there is ways you can offload binary data to the file system, but at the same time, I really wasn't that impressed with this approach. To only be getting a 10% improvement despite majorly reworking the workflow was a bit of a disappointment. So while we did get an improvement, we decided not to actually keep this change. And in hindsight, this was actually a flaw in my tuning process. So here we had a small win. However, later on, as you're going to see, I managed to remove a bottleneck that sped up this process by 50%. And what I neglected to do was to re-baseline with this fix in place. So while shooting this video, I actually ran this test again, and actually, this multiple files per batch concept is now showing a 22% improvement on the speed. So it's definitely worth re-baselining and running through your initial rounds of tuning again, because you might find that what was a small improvement is actually a massive improvement that was being suppressed by something else. Next up, we look to see could we increase the chunk batch size. So I mentioned that we have a nested loop within this workflow. The first one is processing files. The second one is actually a custom chunking function, and then it processes each chunk, and it goes and it generates contextual embeddings, or a little snippet that goes in front of the chunk to ground it in the document itself before it's upserted to the vector store. So this loop over chunks is actually set quite low because we needed to slow down the processing to the LLM that you see here. If you have no idea what I'm talking about, I have an entire video on Anthropic's contextual retrieval, which is this pattern that we have here. But the problem is it really doesn't scale that well. For every single chunk, you're going to an LLM to generate a one-sentence snippet that goes at the start of the chunk. And what we're trying to do here is to scale this RAG system to process thousands of files an hour. So for the moment, we've decided not to use this pattern for RAG at scale. So the hypothesis here then is if we increase the batch size to 200 instead of 20, we should be able to increase the speed of processing of a file because there's less calls to OpenAI, for example. And that test did actually pan out. So I increased the chunk batch size to 200, and I got a 20% improvement on the actual speed of processing of that one file. So this is definitely an improvement that we want to keep going forward. The single biggest win that I had in tuning this system was actually by replacing this vector store node. So by looking at the logs of the benchmark run, you can see that upserting to Supabase took 4 seconds here, it took 3.7 seconds there, another 3.7 seconds here, another 2.8 seconds there. Now we were running a chunk size of 20 at the time, but this vector store node was just taking forever. So then I was thinking maybe it's a problem with the way that we're manually chunking and sending in each chunk into the vector store, because this node is designed to do the chunking using the data loader via the text splitter. So I tested this out quickly using the same file, where we send the full file in and the splitting is done via the node, and then also where we carry out the chunking and pass the chunks in via the loop. And performance-wise, they actually are the same. The next test I did then was to fully remove our custom chunking completely. So I hooked up that direct vector store node here, and interestingly, it was really fast. It only took 1.8 seconds. So the problem is actually with our custom chunking. I've set our custom chunk batch size to 200, just for a like-for-like comparison, and you can see it is quite slow. It was 1.7 seconds with the native module, whereas now this default data loader is really taking its time. It seems to be grabbing the metadata every single time for every single chunk, whereas it's in reality quite static for this document. So compared to the 1.7 seconds, you can see this took 10.9 seconds. So the options here then are to completely remove the custom chunking and just drop in the native node, or to keep the custom chunking, but do a direct database insert into the Supabase vector store. And while I would like to use the native Supabase vector store node, it doesn't actually support contextual embeddings, and we do need this blueprint to support it. So I replaced this vector store node with a direct SQL query into the documents table. And this was created with the help of ChatGPT. And now with this in place, if I trigger it again, you can see that took less than a second. That was lightning fast. So the actual insert into the database was half a second. Now generating the embeddings was 1.2 seconds. So overall, these 4 nodes is essentially as fast as the native Supabase vector store node, but now we can actually support our contextual embeddings, where we can enrich each chunk with a snippet on how that chunk is situated within the document. So relieving this bottleneck gave us a 55% bump in the speed of processing a single file. Now I'm not saying that this vector store node is bad and you shouldn't use it. It's just our particular implementation of it with our own custom chunking was just incredibly slow. And for us, the best approach was to replace it with a direct Postgres query. So you really need to respond to the data that you see in front of you. So within our benchmark tests then, we were now down to 9.2 seconds to process this file that was previously taking 26 seconds. So next up, it was a case of scaling the infrastructure and putting larger quantities of files through this flow to see how it would perform. There are 2 typical approaches to scaling a system. You can vertically scale or horizontally scale. If you're vertically scaling your server, it just means you are adding resources to your server. So you're adding more CPU cores, adding more RAM, adding more disk space, but it's still a single server that's running your application. n8n is a Node.js application, and a key aspect of Node apps is that they're single-threaded. That means they can only run on a single CPU core. So from an n8n perspective, this is your major bottleneck if you're looking to vertically scale your system. You're only ever limited to one CPU core. So you could have a 32-core server, it doesn't matter. And this is where the concept of workers kicks in, which I'll get into in a minute. As opposed to vertically scaling, you can horizontally scale your system. And what that means is you add additional servers into the mix. And then you run your Node.js process or your n8n process on each server. So this way it's much more distributed and the load can be spread across all the servers. So this brings us to the concept of workers and queuing when we come to scale n8n. So you can vertically scale your application by running it in queue mode as opposed to main mode. And what that means is you have your n8n instance, which includes the editor, the APIs into the n8n backend, the various triggers and executors. And then when a task needs to be done, it's added to a queue, which is on Redis, and you have different worker processes. These are all n8n instances that are set to worker mode. And what they do is they poll the queue looking for jobs, and when there's one available, they'll pull it down, process it, and look for another job. So if you're looking to vertically scale n8n on a single server, let's say you have a 4-core CPU, then you could have 4 workers, for example, and each of those workers could max out that CPU core. Now, it's not always a one-to-one between workers and CPU cores. A lot more goes into that decision, but it is a good way of thinking of the bottlenecks of Node applications. So you can take this pattern then and apply it to horizontal as well. So here we have horizontal and vertical scaling with workers. So you have n8n main, which ships items into the Redis queue for them to be worked on. These are executions essentially. And then you have 3 different servers with 3 workers on each, all polling this queue looking for work. They pull down tasks, complete them, and look again for the next task. All of these workers are essentially headless n8n instances. They share the same database and encryption key as the main n8n instance. That way they can successfully complete executions. So this is the way to scale n8n properly. If you are looking to deep dive further into this area, there's a great live stream by Tane and Omar on the n8n channel. It's from 2021, but it's still very relevant. There's also a lot of documentation on the n8n website around scaling n8n, how queue mode works, the various environmental variables that you need to set, the same for concurrency of workers, as well as kind of memory-related errors that you might encounter when you're looking to scale it. I'll leave links for all of this in the description below. If you'd like to try out scaling n8n without getting your hands dirty in server files, command line, or Docker Compose files, then I definitely recommend setting one up on Railway. I'm not at all affiliated with Railway, this is not a sponsored video, but they have a great template that you can use, which provides you an n8n main or primary. It gives you one worker, it gives you a Postgres database and a Redis queue, and it's all configured and ready to go. And once that template is deployed, you can then just simply duplicate workers just by pressing duplicate, and then you can redeploy it, and those workers are then available and actively polling the Redis queue. And this is an example of a workflow that I ran last night, where the primary or the main n8n instance was enqueuing the jobs, and then the workers were polling and pulling down the jobs to work on. So you can see worker 1, 3, 4, 2, and you can see when the worker finishes a job, it then polls and takes the next job. Railway also has this concept of replicas. So if you take worker 3, for example, and if you go to settings, you can see that there are actually 2 instances of this worker running. So my understanding of this is that there's a load balancer behind these workers actually sending jobs to the different instances. Now, I'm not suggesting that you permanently host everything on Railway. This is just a great way to test out scaling without getting your hands dirty. And what's interesting about n8n's performance and benchmarking is that they say it can handle 220 workflow executions per second on a single instance. So that's in main mode. However, the workflow that they tested has 2 nodes, a webhook node and an edit fields node. Whereas we're testing a workflow with 91 nodes, so it's much more of a real world use case. So this is essentially now what our Railway infrastructure looks like. But the question is, how do we send jobs to these workers? Because the way workers operate is that they're looking for executions to run. So if you look at our canvas here of 90 odd nodes, if you were to manually trigger that, that would just be 1 execution. So only 1 worker could ever take that job. So we essentially now need to create a system that can fire loads of files into this Redis queue for the workers to process individually and in parallel. And this is essentially what Alan built when he created the Orchestrator, which I linked to earlier. This Orchestrator is just another n8n workflow. The difference though is it can be manually triggered. It can fetch lots of files from a server, and then in a loop, it essentially calls the RAG ingestion flow. Now you could do this using a sub-execution, but we found actually hitting the webhook of the n8n workflow was a better approach because you got an execution ID back. So this runs really fast in a loop. We're not waiting for a response. And then the act of triggering the webhook adds it to the Redis queue, with the workers then polling the Redis queue looking for jobs to do. And then each individual worker will process each individual file through the workflow. There's a lot more going on in this Orchestrator because Alan had to build another queue on top of the Redis queue to actually keep track of whether executions were successful or whether they failed. And if they failed, there's an automatic retry. And that's important because there's a need for resilience in these systems. It can't be a case that you need to manually dive in and fix a problem if one occurs. Particularly when there's third-party systems involved that might be under load, and if you try it again in 2 seconds time, it'll actually succeed. So the system he built has an Orchestrator queue, jobs are pushed through, picked up by the workers, and if they're successful, it's marked as done on the queue. If they fail, the error is marked and they're retried up to 3 times. I won't go into more detail than that, but if you want a full deep dive into this Orchestrator, then definitely check out Alan's video on it. So with our Orchestrator now in place, we scaled up to 2 workers, we tested 20 PDF files, we included Mistral OCR, which is important, we set our file batch size to 12, and we got a 55% improvement on the speed of processing. So the average time to process the file dropped from 9.2 seconds to 4.1. Now, while that might look like it makes sense, it's half the time with double the workers, it doesn't actually. And the reason for that is concurrency. This is all detailed in n8n's docs, but essentially, each of these workers can actually process more than 1 task at a time, and it's controlled by this concurrency parameter, which defaults to 10. So technically speaking, these 4 workers could process 40 jobs simultaneously. And in my example, I had 2 workers, I added 20 items to the queue. With the default set to 10, all of those items should have been worked on at the exact same time. And originally it was an average of 9 seconds per file to process, whereas now we should be processing 20 files at the exact same time. The total duration should be 9 seconds, which would equate to around half a second a file. I was expecting a much bigger improvement. And you can see that here in our test sheet, where we got our 4.1 seconds, 55% improvement. So I ramped up the number of workers, I changed the batch sizes, but I actually ended up slowing things down by doing so. Which was peculiar because capacity had doubled. We should be absolutely speeding this up. So my hypothesis at this point was that Mistral was our problem. Every file that we were processing was going to the Mistral API to OCR it, get back the data which would then be aggregated and then sent into the vector store. So the next test was to remove Mistral from the equation to see would we speed things up. And rather strangely, we didn't. It was taking 4.1 seconds, it was now taking 3.8 seconds. So Mistral wasn't the problem. And I also knew the bottleneck wasn't in the RAG flow itself. I've already been through this multiple times. So it was actually in the orchestrator that Alan had created. So despite the fact that everything is supposed to run in parallel within the main RAG flow, Alan was actually moving all the files into a processing folder before triggering the actual imports. And this was taking forever because it was all happening sequentially. So all I did was simply disable that and moved it into the RAG flow itself. And this brought our time down to 1.1 seconds for these 20 files. So then I made a few more changes. I increased the batch size to 50 files to run in parallel, because at this point I had 4 workers with replicas, so I had massive capacity here. I could possibly process 80 files in a go. So I boosted it to 50, and I got the time down to 0.7 seconds per file to import. So with 7/10 of a second to process a file, we actually have too much resources here. We can process up to 80 executions in parallel, having 4 workers each with a replica and a concurrency set to 10. So we could reduce our server capacity pretty safely. So the last thing to do then was to re-enable Mistral. So I tested it with 200 files with the batch size of 50, and the processing time jumped from 0.7 of a second per file to 1.4 seconds, which is incredible really if you think about it. These PDF files have up to 50 pages, and Mistral is absolutely lightning fast when it comes to processing concurrently as well. So this was a huge win, because if you want good quality embeddings in your vector store, you really should OCR everything. And these are the final tests when ramping up with Mistral. And again, it's so consistent. We threw 20 files at it on a number of occasions and 200 files. Every single time it averaged out at 1.4 seconds per file. So just incredible. We spent over 100 hours scaling and tuning this system, and there are just so many lessons that we learned along the way that hopefully will be of help to you if you're looking to tune your own workflows. And the first is, you really need a systematic approach to analyze your workflows to find the bottlenecks. Here I used a structured Google Sheet, and this is a very good way to be able to track different configuration settings and the results that you're getting. And you will really need to dive deep into the logs to find out where the actual bottlenecks are, so that you can start making some hypotheses and assumptions, and then you can test those assumptions. And I think this is a good 7-step structure that you can work off. So you create your benchmarks based off your existing flow, find the bottlenecks like I just described, generate your hypotheses, experiment, change things, and then test again, and then you need to analyze and decide whether you want to keep it or not. And the big mistake I made was that I didn't re-baseline when I made some big steps forward to recalculate the improvements from some of the previous ideas that I had. The second learning is that it really is a custom job. There are general best practices that you can follow, but you really need to immerse yourself in the workflow, in the data, in the third parties you're integrating with, in the files that you're processing, to really figure out what actually is happening. And as I found on this journey, increasing resources isn't always the solution. I started off with 2 workers, and when I increased it to 8 workers, I actually slowed things down. So you really need to analyze the flow to figure out what actually is going on. Because once that's operating efficiently, then when you add resources, you should see the scale kick in. n8n workflows are all about connecting third-party systems. And generally speaking, these third-party systems don't want you overloading them. So they can rate limit you, they can throttle you. And a lot of the time, the reason you might not be seeing savings is because they may have locked it down at the API level on the other side. And at times it makes sense to go direct to the source. Try to avoid the API. I did that with Supabase, where I just piped directly into the Postgres database through their transaction pooler. Now that's not necessarily for the faint-hearted, because it is more technical, and we ended up needing to get a dedicated pooler to handle so many concurrent connections. So it doesn't always make sense, but there are lots of ways to solve a problem. We had the same issue with Google Drive, where we were getting buggy and cached responses from the Google Drive node. So eventually we just binned that idea and we set up our own SFTP server and loaded up our files to it. So again, we bypassed all of the various APIs to access the file server, and now it's just a straight SFTP connection to retrieve the files. It's definitely worth focusing on the low-hanging fruit. My first idea that I had to increase the performance of this flow was to increase the batch size in the loop over files node. That required major restructuring and testing of the workflow, and in the end we didn't even use the changes. So I really should have started somewhere easier. It's also good to know when to quit, because there is no end to this. We got this to the point where we can process a file in 0.7 seconds. We could keep at it. We could get it down to 0.4 or 0.2 or 0.1. But there is the law of diminishing returns here. And operating a batch import at 0.7 seconds that is resilient to failure is most likely enough for the vast majority of use cases. The further you go down this track of scaling, the more you'll realize that you probably need to be self-hosting. And that's not just n8n. It may get to the point where you should be self-hosting Supabase, your SFTP server, a Postgres database. I hope you enjoyed the video and you learned something about scaling and tuning your own n8n workflows. If you'd like to get access to our Orchestrator or our RAG ingestion pipelines, then check out the link in the description to our community, the AI Automators, where you can join hundreds of fellow automators all looking to leverage the latest in AI to automate their businesses. Thanks for watching, and I'll see you in the next one.